Hello, we now continue our quick overview of the history of cosmology. In the last module, we learned how expansion of the universe, observational discovery, and general relativity, which provided a theoretical framework for cosmology, really established it as a science. Something else, however, happened in 1930s that's of considerable importance, and that is discovery of the dark matter by Caltech physicist and astronomer Fritz Zwicky, who applied simple Newtonian mechanics to motions of galaxies in a coma cluster. Their kinetic energy has to be balanced by the binding energy, and so he could deduce how much mass is needed in order to keep cluster together. So he found out that you need 400 times as much invisible matter that does exert some gravitational influence than what's actually seen in stars. Similar thing was found by another astronomer, Sinclair Smith, for Virgo cluster a few years later. But at that time, nobody took this seriously, because this was just a too outrageous statement, and there was no other evidence for it. Until 1970s, when sufficient evidence has accumulated that dark matter could no longer be ignored. And now essentially everybody believes in its existence for good reasons, which we'll cover later. Dark matter is today a key ingredient in the models of structure formation, but its exact physical nature is not yet understood. And this is one of the outstanding problems of physics today. Meanwhile, observational astronomers, following first Hubble, but then his followers, including Alan Sandage, tried to establish what kind of relativistic cosmological model we live in. Hubble designed a set of cosmological tests, how observations of distant galaxies can be used to determine global geometry. The foremost of those was so-called Hubble diagram. Remember, that's the plot of relative distance versus velocity for galaxies far away from us. And near us, this is very close to a straight line. Now, as you go further deeper in space, relativistic effects start playing a role, and the line deviates from straight in a way that depends on values of cosmological parameters. So Sandage and his collaborators tried very hard to do this, using the brightest cluster galaxies as what they call standard candles, assuming that their internal luminosity is constant. And that basically failed, because galaxies are not constant. They evolve, they're made of stars, stars evolve, galaxies merge. And so until mid-90s, Hubble diagram was not considered as a serious cosmological test. But then things changed considerably. Galaxy evolution really became forefront of cosmology in late 1970s and 1980s, and this was in part due to realization that we must understand how constituents of galaxies evolve, and therefore galaxies themselves, before we can use them for cosmology. But it's also containing a number of interesting questions on its own. And studies of this were enabled by development of modern instrumentation, ending up in charge-coupled devices. And a lot of that was done at Palomar Observatory. Here are some of the famous astronomers who developed early instruments to study distant universe. Meanwhile, on theoretical front, Fred Hoyle, Hermann Bondi, and Thomas Gold came up with a new idea called the steady-state cosmology. Remember that cosmological principle says that the universe is same all places in all directions. Well, they said also it at all times. But because it expands, new matter has to be created in order to fill up the gaps. And the mechanism for this was not specified, and that was clearly seen as a weakness. But in that sense, the universe would always look the same. Keep expanding, but always look the same. And there are cosmological tests that can distinguish between those two. In part, this was trying to respond to the extrapolation of the galactic, cosmic expansion to what we now call Big Bang, which at least Hoyle found distasteful and gave it a name. But Big Bang theory actually made some important predictions. George Gamow and his colleagues Alpher and Herman actually considered what Lemaitre thought was primitive atom and ask what will be the physics if universe is so hot and dense. And so what universe will do is what stars do in their cores, which is convert hydrogen into helium, or heavier elements. And they did develop that along with Hans Bethe and call it alpha, beta, gamma theory, but it turns out that they can predict the formation of elements all the way up to helium. In other words, just hydrogen and helium. However, there should have been an afterglow of this cosmic thermonuclear explosion, which, thanks to the redshift stretching of the photons, now will not be gamma rays, but will be really microwaves with a black body temperature of 5 degrees Kelvin or so. Well, this was actually measured in 1965 by Penzias and Wilson, who deservedly got Nobel Prize for this discovery. The cosmic microwave background remains as one of the touchstones of cosmology. Today we can measure it with space instruments, and its spectrum is, as predicted by theory, pure black body radiation, which is now measured with exquisite precision, and it might be actually the purest black body spectrum that we have measured anywhere. Another prediction of the Big Bang theory is that there will be the abundances of very light elements. I said it will only make helium, but that's not quite true. It will also make trace amounts of lithium and maybe a touch of boron and beryllium, but also different isotopes of helium and hydrogen, deuterium and helium-3. So here we have on the left plot of the helium mass fraction in star-forming galaxies plotted against their oxygen abundance. Oxygen is only made in stars. So if both helium and oxygen were made in stars only, then this plot would be a line going through the origin of 0 point. But instead of that, there is an intercept. The 0 point from which starts is about 0.24 mass fraction of helium, and therefore stars must begin with that much helium, and the only place that helium can come from was from primordial nucleosynthesis. Models of primordial nucleosynthesis have been developed with great precision, and now they're compared with observations. The plot on the right shows theoretical predictions as functions of the density, baryon density of the universe, and the blue band shows where that measured value is. So it all is consistent with what we now believe are the right cosmological parameters, and this is also seen as one of the great pieces of evidence in favor of the Big Bang cosmology. In the meantime, another important discovery happened, or set of discoveries really. After the World War II, thanks to the radars, radio astronomy was born. And radio astronomers started mapping the sky in radio wavelengths, seeing their sources, whose nature was at first unknown. And astronomers like Walter Baade and Rudolf Minkowski obtained optical counterparts of some of these sources and discovered some of them are actually quite far away, implying that given the observed flux, internal power and luminosity of these objects must be enormous. This was a very surprising and important discovery. Even the optical, signs of something interesting were already there. In 1940s, Carl Seifert, for his PhD thesis, observed bright nuclei of nearby spiral galaxies and found they have these somewhat unusual spectra with very broad emission lines, and their nature was not understood at the time. But it took really a combination of optical and radio astronomy with identification of quasars to really drive this point home. Cyril Hazard was one of the radio astronomers who obtained precise measurements of few quasi-stellar sources and their positions. Alan Sandage and others at Palomar obtained their optical counterparts, and Martin Schmidt and his collaborators figured out what's going on. Namely, from the shift of lines in the spectrum, they figure out they must be very far away. Remember, the faster objects recede, the further away they are. Well, this implied enormous distances to quasars, which then implied that their internal luminosities are huge. So you have an object that may be 10 times, 100 times, 1,000 times more luminous than the entire galaxy of stars. And that luminosity comes from regions smaller than the solar system. Martin Schmidt made it to the cover of Time magazine. I think he was the second astronomer with that honor. The first one was Harold Shapley. Meanwhile, another important line of study was happening, namely discovery of the large-scale structure of the universe. It really began in 1930s with Harold Shapley, Zwicky, and their collaborators starting to map how galaxies clump in space. It was clear that they're not purely randomly distributed. And through the 50s, the 70s, more evidence was accumulated, and it was obvious that galaxies are clumped in clusters and less dense but more extensive structures. However, the really most important new development was measurements of redshifts, which imply distances to vast numbers of galaxies. First, thousands, but now they're really hundreds of thousands. Gerard de Vaucouleurs, who was a famous observational astronomer, also pointed out that our immediate extragalactic neighborhood forms what he called a local supercluster, of which we're one part, and Virgo cluster is the center. It's an elongated structure in the sky, as seen in projection here. And this was an indication of structures that are larger than anything seen before. So today, of course, we know this with a much greater precision. And here is the projected map of density of galaxies from the Sloan Digital Sky Survey, a modern redshift survey, and shows these filaments and voids and bubbles, which are important features of the galaxy distribution that we will study later on.